SpaceX's rise begins with a problem that sounded almost philosophical. Space was too expensive, too slow, and too protected by tradition. For decades, orbit had been treated like a rare luxury, something reserved for governments, massive budgets, and long timelines. The idea that a private company could build orbital-class rockets, launch often, and reduce costs dramatically felt unrealistic to most of the industry. And yet, that's exactly what SpaceX attempted: turn spaceflight into something closer to engineering and manufacturing, and less like one-off national projects. The origin story: a vision shaped by frustration. Before SpaceX became a household name, it existed as a conviction. If rockets could be built more like products, costs would fall. The core belief was simple but radical. Rocketry had become trapped in a cycle of complexity and low launch frequency. When you launch rarely, you don't learn fast. When you don't learn fast, systems remain expensive and fragile. When systems are expensive and fragile, you launch rarely. SpaceX wanted to break that loop by doing the opposite: design for manufacturability, launch frequently, learn quickly, and iterate relentlessly. SpaceX was founded in 2002 with a clear mission: enable humanity to become a multi-planet species. But the first step was more practical: build a rocket that could reach orbit at a fraction of the cost. It's important to understand how audacious that was at the time. Rocket engineering is unforgiving. There are no partial victories. Either your vehicle performs through every phase: ignition, ascent, staging, guidance, orbital insertion, or it fails. A startup can survive imperfect software. A rocket startup cannot survive repeated explosions without either extraordinary funding or extraordinary stubbornness. SpaceX had both. Choosing vertical integration: control the hard parts. One of SpaceX's earliest defining choices was to build a large portion of the rocket in-house. Many aerospace programs depend on huge supplier networks, with components coming from different contractors, each with their own processes and incentives. That approach can be effective for national programs, but it tends to be slow, expensive, and complicated to coordinate. SpaceX took a different path: vertical integration, simplified supply chains, and strong internal ownership of critical systems. This decision was risky because it meant SpaceX had to master many engineering disciplines simultaneously: propulsion, structures, avionics, guidance, manufacturing, software, ground systems, testing. But it also created a powerful advantage: speed. If something broke, SpaceX could redesign it without wading through layers of contractors and contract negotiations. If a component was too expensive, SpaceX could build a cheaper one. If a part needed improvement, engineers could walk into the factory and change the build. In aerospace, that kind of tight feedback loop is rare. SpaceX treated it as essential. Falcon 1, the brutal school of reality. SpaceX's first rocket, Falcon 1, was meant to be a relatively small orbital launcher. It wasn't the final dream, it was the first proof. And proving you can reach orbit is the moment when you stop being a company with potential and become a real aerospace player. But the path was painful. The early Falcon 1 flights failed. Each failure was expensive, public, and emotionally crushing. Rockets don't fail politely. A failure means you lose the vehicle, the payload, the time, and often the confidence of customers. For a young company, a string of failures can end everything. This is where SpaceX's culture of iteration was tested. Many organizations respond to failure by slowing down, becoming cautious, and spreading responsibility so no one is to blame. SpaceX responded by doubling down on learning, fixing root causes, changing processes, testing more aggressively, and pushing toward another attempt. Behind those flights was a crucial idea: testing is the truth. In rocketry, simulations are never enough. You can model physics, but you can't model every vibration, every manufacturing variance, every thermal condition, every interaction between subsystems. SpaceX began building a culture where hardware is tested often, pushed hard, and improved continuously. The near-death moment, one launch away from collapse. The most dramatic chapter of early SpaceX is the period when the company was reportedly close to running out of money. In the startup world, near-death is common. In the rocket world, it's existential. Costs are huge, and investors are cautious because the downside is obvious and the timeline is long. SpaceX had to survive a stretch where success was not guaranteed, and the market did not fully believe in private orbital capability. The key to the story is that SpaceX didn't need a perfect track record. It needed one undeniable win: orbit. The breakthrough. Falcon 1 reaches orbit 2008. When Falcon 1 finally reached orbit, it did more than deliver a payload. It delivered credibility. That success meant SpaceX had crossed the hardest threshold in commercial space, proving the company could build a launch vehicle that works. The idea became reality. Customers, government agencies, and the broader aerospace world had to update their assumptions. This is the first major milestone in SpaceX's rise. It created the psychological turning point. SpaceX is not just ambitious, SpaceX is capable. NASA and the shift toward scale. For SpaceX to grow beyond a small launcher, it needed serious customers and serious missions. NASA's interest in commercial cargo services, especially after the space shuttle era, created an opening for new private capabilities. For SpaceX, NASA contracts were not merely revenue, they were validation and structured opportunities to prove performance repeatedly. But SpaceX did not simply become a contractor. It used that relationship as a proving ground to build systems that could scale. Bigger rockets, larger payloads, higher reliability. The cultural blueprint: speed, risk tolerance, and learning. By the end of this phase, SpaceX had already established the culture that would define its rise. Iterate quickly, don't wait years to find out what broke. Own the stack, build and improve core systems internally. Test aggressively, hardware tells the truth. Accept failure as tuition, learn fast and move forward. Aim higher than comfort, build what others say is impossible. Falcon 1 was not the end goal, it was the opening chapter. The real rise would come when SpaceX tried to do what had defeated many: build a reliable, high-performing, medium to heavy launcher and fly it often. That rocket was Falcon 9, and the deeper dream, reusability, was still ahead. Once SpaceX proved it could reach orbit, the company entered a different phase. The early period is about survival and credibility. The next period is about dominance through scale, building rockets that launch often, transporting cargo and humans, and making reusability real. This is where SpaceX stopped being a surprising startup and started becoming the center of gravity in global launch services. 1. Falcon 9, designing for reliability and repetition. Falcon 9 was the vehicle that turned SpaceX from a demonstration into a system. A rocket that flies once can be a miracle. A rocket that flies repeatedly becomes an industry. Falcon 9 was designed with a strong emphasis on repeatable manufacturing, simplified architecture, and operational efficiency. It wasn't perfect early on, but its growth was defined by iteration, upgrades, improvements, and experience gained through frequent launches. In aerospace, repetition is power. Frequent launches create faster learning cycles, lower cost per mission through streamlined operations, higher confidence from customers, refinement of quality control and flight software, a reputation built on performance, not promises. SpaceX's rise is, in many ways, the story of how launch cadence became a competitive weapon. 2. Dragon, proving SpaceX could deliver to orbit, then to station. The Dragon spacecraft became another crucial pillar. Rocket launches are impressive, but spacecraft operations, rendezvous, docking, safe cargo delivery, and recovery are a different level of complexity. Dragon gave SpaceX a pathway into logistics and mission services, not just launch. With Dragon, SpaceX was building more than a capsule. It was building a relationship of trust, proving the company could serve NASA-level missions and operate within strict safety cultures while still maintaining its speed-focused identity. This is where SpaceX began to show a rare skill: operational maturity without losing engineering aggression. Most organizations lean heavily toward one side. SpaceX tried to hold both. 3. The reusability revolution, the moment rockets stopped being disposable. The biggest reason SpaceX's rise is considered historic is reusability. For most of spaceflight history, rockets were treated as disposable. Disposability locks in high costs. If you throw away the biggest parts of the vehicle every launch, your economics will always be harsh. SpaceX's bet was that you could land boosters, refurbish them, and fly again with enough reliability that reuse becomes normal rather than heroic. Making that real required solving multiple hard problems at once: controlled descent through the atmosphere, precision guidance and landing burns, strong structures that survive launch and re-entry stress, thermal and mechanical durability, rapid inspection and refurbishment processes, operational consistency that scales. The first successful booster landings were dramatic not just visually, but economically. They signaled that the cost structure of launch could change. The industry had talked about reusability for decades. SpaceX made it routine. And once routine arrives, it reshapes competition. Competitors may match performance, but matching the economics and cadence is far harder. 4. The fly, land, refly loop becomes the moat. Reusability wasn't a single achievement, it was a system. The system created a loop: land the booster, inspect and refurbish it, learn what degraded and why, improve design and manufacturing, reduce refurbishment time, fly again, repeat. This loop created compound advantage. Each flight made SpaceX better not only at launching, but at operating. The more you fly, the more you learn. The more you learn, the faster you improve. The faster you improve, the more you can fly. Over time, that compounding learning loop became one of SpaceX's greatest strategic advantages. 5. Starlink, changing the business model of a rocket company. SpaceX didn't only want to sell launches, it wanted a demand engine that could justify constant launches. That's what Starlink provided: a massive satellite constellation requiring frequent deployment. Starlink became both a customer and a strategic asset. This is important because it changed SpaceX's leverage. SpaceX no longer depended only on external customers for launch demand. It could plan launches around its own deployment schedules. High cadence strengthened the Falcon 9 operational machine. Launch frequency supported cost reduction and reliability learning. Starlink also brought a new dimension: SpaceX as a service provider in global communications. That broadened SpaceX's identity. It was no longer just an aerospace manufacturer, it was becoming an infrastructure company. 6. Human spaceflight, the ultimate trust milestone. Crewed missions are the hardest validation because the stakes are absolute. When SpaceX became a provider of crew transport, it signaled that the company could meet the highest standards of safety and reliability in partnership with NASA. This wasn't just engineering achievement, it was institutional trust. That trust took years of development, testing, reviews, and operational discipline. It showed SpaceX could integrate its fast culture with a safety-critical framework that demanded thoroughness and consistency. In the story of SpaceX's rise, human spaceflight is a graduation moment, not because SpaceX became perfect, but because it demonstrated it could deliver under the most demanding conditions. 7. Starship, the biggest bet. turning spaceflight into true mass transport. If Falcon 9 is the machine of the current era, Starship is the gamble for the next era. Starship represents an attempt to create a fully reusable, extremely high-capacity system designed for deep space missions and large-scale transport of cargo and potentially people. The ambition is enormous. If a fully reusable heavy-lift system works as intended, it could reduce cost per kilogram to orbit drastically and enable missions that are currently too expensive or complex. It could also unlock large-scale satellite deployment, rapid space station construction and resupply, lunar logistics at meaningful scale, new commercial markets that only exist when launch becomes cheap and frequent. But Starship is also a reminder that SpaceX's rise is fueled by risk. Starship development has involved aggressive testing, iterations, and learning through failure. That approach is controversial, but it's consistent with SpaceX's core philosophy: build, test, break, improve, repeat, until it works. 9. Why SpaceX rose when others struggled. SpaceX succeeded where many efforts failed because it combined several strengths at once: engineering ambition without waiting for perfect certainty, manufacturing mindset rather than bespoke craftsmanship, vertical integration that allowed speed, high launch cadence that created faster learning, reusability that changed economics, internal demand, Starlink, that supported frequent launches, operational discipline strong enough for NASA partnerships. Most competitors have some of these, few have all. 10. The deeper meaning of SpaceX's rise. SpaceX's rise isn't only about rockets. It's about changing the default belief of what is possible. Before SpaceX, the assumption was that orbital launch would remain expensive, slow, and government-centered. After SpaceX, the assumption shifted towards private industry can lead in launch innovation, reusability can be operational, not theoretical, launch frequency can be high and improving, the economic curve can be pushed down through iteration and scale. SpaceX didn't just join the aerospace industry, it changed the aerospace industry's tempo. 10. The story that continues. The rise of SpaceX is still unfolding. The biggest chapters, fully reusable heavy lift, sustained lunar logistics, and Mars cargo capability, are still ahead, but the shape of the rise is already clear. SpaceX began as a long-shot startup trying to reach orbit. It became a high-cadence launch provider. It pioneered operational booster reuse. It built a satellite network to fuel demand. It proved it could fly humans safely, and it is now attempting the most ambitious step: a fully reusable ship designed to make deep space travel less like a rare event and more like a repeatable system. That is the real rise, not a single breakthrough, but a series of compounding loops: engineering, manufacturing, operations, learning, each one reinforcing the next.
SpaceX's rise changed shape the moment reusability stopped being a stunt and became a habit. In the beginning, a landing was a headline. Later, landings became a line item, something you expected to happen unless a mission had unusual constraints. That transition matters more than almost any single test, because in aerospace, the difference between possible and repeatable is the difference between a breakthrough and a business. The economics of not throwing away your best hardware. For most of spaceflight history, the world accepted a painful truth. The rocket is the launch. You build a giant machine, ignite it once, and then you discard much of it into the ocean, or burn it up, because recovery was considered too hard, too risky, or not worth the mass penalty. That assumption locked in high costs. It also locked in low flight rates, and low flight rates lock in low learning. SpaceX's reusability program was, at its core, an attempt to flip the entire system. Don't treat boosters as disposable fireworks. Treat boosters as aircraft-like assets. Fly more, learn more, improve more, and reduce cost over time. That sounds obvious now, but it wasn't obvious to the industry culture that grew up around one-and-done launch vehicles. The key invention was not the landing, it was the process after the landing. The internet loves the moment the booster touches down. That's the dramatic part. But the true innovation is what happens next: inspection, repair, refurbishment, and scheduling the next flight. If a booster lands perfectly but takes a year to refurbish, the economics are weak. If it lands and can fly again quickly, reusability becomes a compounding advantage. Over time, SpaceX built a loop: fly to land to inspect to replace/refurbish what needs it to improve design to reduce wear to fly again. This loop is the same logic that made aviation affordable. The cost of the machine is spread over many flights, and every flight teaches you how to reduce downtime. Cadence becomes a competitive weapon. In aerospace, cadence is not just a schedule, it's power. Higher flight rates create faster operational learning, how to avoid small errors that cause big delays, better manufacturing rhythm, suppliers, inventory, and production lines stabilize, more confident customers, a vehicle that flies often becomes familiar, more opportunities to iterate upgrades, you get more real-world data sooner. This is where SpaceX began breaking away from competitors. The company wasn't only launching, it was building an industrial tempo. The reuse record culture, proving that boosters can fly again and again. As booster reuse matured, it created a new form of proof: flight count. The number of times a single booster can fly tells the world whether refurbishment is truly getting easier and whether the hardware is truly durable. By February 2026, SpaceX boosters were reaching reuse numbers that would have sounded absurd years earlier. Space.com reported boosters flying 31 and 33 times in a single day of launches, setting a reuse record. And just days earlier, Space.com described a Falcon 9 booster landing after its 26th flight during a Starlink mission, again highlighting how routine high flight count recovery has become. These aren't just fun facts, they are evidence that the refurbishment pipeline has become efficient enough to support repeated use, which is exactly the point of the reusability strategy. Reliability plus reuse, the hard balance SpaceX had to learn. Reusability introduces new risks. You are flying hardware that has already experienced extreme stress. In aviation, this is normal. In rocketry, it was psychologically uncomfortable for many customers at first. SpaceX had to earn trust through performance. That meant building a culture where reuse is treated without casualty. It has to be managed like a system: standardized inspections, clear life limits on components, upgraded designs to reduce refurbishment labor, strict acceptance criteria, data-driven decisions about what is safe to refly. Reusability only creates a moat if it remains reliable, and reliability is not achieved by optimism, it's achieved by discipline. The fleet effect: boosters as a managed portfolio. As SpaceX accumulated multiple flight-proven boosters, it gained a new capability: booster assignment as portfolio management. Some missions need maximum performance, some can accept heavier landing fuel reserves, some require special trajectories. When you have a fleet, you can assign the right booster to the right mission and keep your schedule resilient. This is an underrated point. A reusable system isn't just cheaper per flight, it's also more flexible. Flexibility is valuable when customers pay for certainty. The broader result: SpaceX forced the industry to reevaluate normal. Once SpaceX demonstrated routine landing and reuse, the global launch industry had to update its mental model of cost and cadence. Competitors could still compete on niche capabilities, national security priorities, or unique orbits, but the baseline expectation changed. Rockets that can't reuse hardware, at least partially, look economically disadvantaged in a world where SpaceX can.
SpaceX's rise is often told as a rocket story, but the most strategic move the company made may be its decision to become its own biggest customer. That is what Starlink represents: demand that SpaceX controls at the scale of thousands of satellites. When you own your demand, you don't merely respond to the market, you shape it. Why Starlink is a business model breakthrough. A traditional rocket company sells launches to external customers. That creates dependence. Customers are cyclical, budgets change, programs get delayed, demand is lumpy. Starlink changes that. Starlink turns SpaceX into a vertically integrated launch plus payload plus service system. The rocket is not only a product, it's also the delivery mechanism for SpaceX's own network. This creates a powerful flywheel. Starlink needs launches. SpaceX launches more often. More launches, SpaceX learns faster and reduces cost. Lower cost plus higher cadence, Starlink satellites can be deployed faster and cheaper. A bigger Starlink network, more revenue and strategic leverage. More revenue, more investment in rockets and satellites. Repeat. The scale is hard to comprehend. By early 2026, Starlink had grown into the largest satellite constellation ever assembled. Space.com reported over 9,700 active satellites after February 2026 launches. Wikipedia's Starlink summary, updated January 2026, reported over 9,422 satellites in LEO as of that update. The exact number shifts constantly because satellites are launched, deorbited, replaced, and upgraded. But the core truth remains. Starlink is now a mega constellation of a size that creates strategic gravity. Starlink turns launch cadence into a factory rhythm. Starlink is not only a satellite network, it is a production system. SpaceX manufactures satellites, launches them frequently, and manages a growing infrastructure of ground stations and user terminals. In this system, rockets become logistics vehicles, serving SpaceX's own deployment schedule. This is how SpaceX achieved launch frequency that looks almost unreal. Space.com reported SpaceX completed 165 orbital rocket launches in 2025, breaking its annual record again. Payload Space's 2025 launch attempt breakdown also listed SpaceX at 170 launches total for the year, including Starship, and 165 Falcon 9 launches. Different outlets may count categories slightly differently, but both reinforce the same picture. SpaceX is launching at a cadence that no other commercial organization matches. A monopoly-like advantage and the durability test. When one provider launches far more than everyone else, it begins to look like a monopoly in operational terms, even if competition exists legally. Reuters' Breaking Views column, Feb 26, 2026, described SpaceX's nascent monopoly facing a durability test and reported estimates that Starlink drives a large share of SpaceX's overall value and revenue momentum. This matters because SpaceX is no longer judged like a niche aerospace company. It is judged like infrastructure. Geopolitical reliance concerns, national alternatives and diversification efforts, regulatory pressure, and competition from other mega constellations such as Amazon's Kuiper. In a strange twist, SpaceX's success creates its own pushback. The more important Starlink becomes, the more governments and competitors feel pressured to build alternatives. Starlink also changes the narrative of SpaceX's mission. SpaceX talks about Mars and deep space. Starlink talks about internet, connectivity, and national resilience. Together, they form a two-track story, a visionary mission that inspires talent and attention, a practical business that generates cash flow and launch demand. This combination is unusually powerful. Many visionary aerospace projects struggle because they cannot fund themselves at scale. Starlink gives SpaceX a pathway to fund aggressive engineering while staying operationally active. The strategic result is SpaceX becomes harder to disrupt. A competitor trying to beat SpaceX now has to compete on multiple fronts: launch vehicle capability, reusability and cadence, satellite manufacturing and deployment, network operations, customer terminal production, service pricing, and performance. That is an enormous stack to replicate. You can build a rocket and still lose to a company that also owns the biggest satellite network and can launch its own payloads constantly. Starlink is not extra.
It is the center pillar of the SpaceX empire-building phase.
If Falcon 9 is SpaceX's operational masterpiece, Starship is SpaceX's wager on a new world. Starship aims to do something the industry has wanted for decades, but rarely approached seriously: a fully reusable, extremely high-capacity launch system that behaves more like a transport vehicle than a disposable rocket. This is a different type of challenge. Falcon 9 proved that partial reuse can be routine. Starship attempts to prove that near total reuse can be routine, and that you can do it at a scale that changes what is economically possible in orbit. 1. Why Starship matters. It changes the unit economics of big missions. Many space ideas are limited not by physics, but by cost per kilogram to orbit. If Starship works as intended, it can unlock categories of mission planning that currently feel too expensive: large-scale satellite deployment and replacement, heavy industrial payloads for space infrastructure, rapid logistics to orbit, more frequent lunar cargo deliveries, serious Mars cargo campaigns over multiple launch windows. In other words, Starship isn't just a bigger rocket. It's a bet that the bottleneck of space, cost and cadence, can be pushed down another major step. 2. The development style is intentionally aggressive. SpaceX's own updates page describes Starship flight tests and outcomes in detail, including a Flight 9 and Ship 36 report, and specifics about liftoff timing and test objectives. Independent timelines also summarize key milestones. For example, coverage noting the towered chopsticks catching the booster during an October 13, 2024 test flight. And Wikipedia's list of Starship launches page reflects ongoing iteration and multiple blocks and vehicles flown as the program evolves. The exact details and interpretations vary by source, but the broader pattern is clear. Starship is being developed like a prototype program that expects iteration, not like a traditional aerospace program that tries to avoid public failure at all costs. 3. The regulatory and public trust layer becomes huge. The bigger and more frequent Starship tests become, the more the program intersects with regulation, environment, and public tolerance for risk. Falcon 9 matured into a high-cadence system partly because its operations became predictable and controlled. Starship must reach a similar state to be truly transformative. A reminder of how delicate this can be, Space.com noted that SpaceX had paused some Bahamas area Falcon 9 landings after debris from a Starship upper stage breakup scattered over parts of the Caribbean in early 2025, and that later assessments cleared resumed operations. This illustrates a key truth. In the high-cadence future, it's not enough to innovate, you must also maintain permission to operate. 4. Why Starship is a second rise challenge. SpaceX already won the first rise. It became the dominant launch operator by making reuse and cadence real. Starship is about whether SpaceX can win a second rise, redefining what normal looks like for heavy lift and deep space logistics. The risk is real. Technical difficulty, heat, re-entry, rapid reuse at scale, regulatory constraints, supply chain and manufacturing ramp complexity, operational maturity requirements that grow with payload and flight rate. But the upside is historic. If Starship becomes operationally reusable at high cadence, space infrastructure becomes more feasible. If it doesn't, SpaceX still remains dominant through Falcon 9, Dragon, and Starlink, but the dream of space as transport remains partly locked. 5. The meaning of SpaceX's rise, reframed. With Falcon 9, SpaceX proved a private company could build a reliable, reusable launcher and fly it constantly. With Starlink, SpaceX proved a rocket company could become an infrastructure company. With Starship, SpaceX is attempting to prove something even bigger. Space access can scale like an industry, not like an event. That is what the next chapter is really about. Not a single rocket, not a single mission, but a shift in the default assumption again. SpaceX's rise reaches a different level when you stop seeing rockets as rare events and start seeing them as a rhythm. In the early days, a launch was an achievement. In the cadence era, a launch is a unit of work, planned, scheduled, repeated, and improved like a factory output.
This shift is not just operational, it is strategic. Because in aerospace, the company that flies the most often usually learns the fastest. And the company that learns the fastest usually becomes the standard everyone else has to chase. 1. Cadence is the hidden force behind dominance. In most industries, the winners are not only the inventors, they are the operators. SpaceX built a launch operation that behaves more like logistics than spectacle. The best way to understand this is to compare it to aviation. Early airplanes were fragile and experimental. Modern airlines are systems. Maintenance, schedules, standardized checks, trained teams, reliable processes, and constant repetition. SpaceX has been pulling rockets in that direction. It didn't happen in one miracle moment. It happened through thousands of small upgrades. Streamlined pad processing, faster propellant loading procedures, standardized booster inspection routines, improved ground support equipment, refined flight software and mission planning, better coordination across production and launch sites. Cadence becomes a compounding advantage because every mission generates lessons. If you launch once in a while, lessons arrive slowly. If you launch constantly, lessons arrive every week. Over time, that difference becomes an uncatchable gap. 2. Reuse records are the scoreboard of the Cadence era. Cadence is not just how often you launch, it's how often you can reuse the same expensive hardware without losing reliability. By early 2026, SpaceX was pushing booster reuse into numbers that once belonged to science fiction. Space.com reported Falcon 9 boosters flying 31 and 33 missions, setting new reuse milestones in February 2026. These reuse counts matter because they signal multiple things at once. The booster design is durable enough to survive repeated extremes, refurbishment processes have been simplified, inspection workflows have become efficient, the company has gained confidence in flight-proven hardware. A reusable rocket is not automatically a cheaper rocket. It becomes cheaper only when the refurbishment pipeline becomes fast, predictable, and repeatable. High flight counts are evidence that SpaceX is turning boosters into long-lived assets rather than single-use machines. 3. Launching becomes a supply chain, and SpaceX controls most of it. SpaceX's operational advantage is partly about vertical integration. If your rocket depends on many slow external contractors, your schedule becomes fragile. SpaceX built a system where the core stack, engines, structures, avionics, software, and much of the manufacturing can be coordinated inside one organization. This allows rapid iteration and also reduces the number of waiting points where progress stalls. The operational result is less glamorous than rocket landings, but more important: schedule resilience. When you can replace a part quickly, upgrade a component without renegotiating a contract, and adjust production rhythm to match launch needs, you can keep momentum even when problems occur. In a cadence-driven industry, resilience is a weapon. Customers do not only buy performance, they buy confidence that you will deliver on time. 4. The most important customer is sometimes yourself. This is where Starlink becomes inseparable from Cadence. SpaceX is not just selling launches, it is feeding a constant deployment pipeline. Starlink acts like an internal demand engine. It creates reasons to launch repeatedly, which keeps the Falcon 9 machine warm. This is one reason SpaceX's annual launch totals have looked so extreme. Space.com reported SpaceX achieved 165 orbital launches in 2025 as a record. Other trackers and summaries may present slightly different totals depending on what they count: attempts versus successes, Falcon versus Starship, etc. But the main reality is consistent. SpaceX has built a launch rhythm unmatched by any other private organization. The strategic effect is profound. SpaceX's own constellation makes SpaceX less dependent on outside market cycles. If commercial customers slow down, SpaceX can still launch to expand, replenish, and upgrade its network. 5. Pads, turnaround time, and the logistics mind.
A subtle but powerful piece of the cadence story is pad turnaround time. Faster turnaround means you can launch more often without building endless new pads. It also means you have learned to run launch operations like a high-performance crew. Quick setup, disciplined procedures, and consistent execution. SpaceX's public launch listings show a steady stream of upcoming missions and reflect a schedule that resembles a shipping timetable more than a traditional aerospace calendar. This is not just a brag. A dense schedule forces improvement. When you're always close to the next launch, you cannot afford bureaucratic habits. You must simplify. You must standardize. You must get good at the boring details. That is how industrial leaders are made. 6. Cadence shifts the industry's psychology. When SpaceX launches frequently, it changes what customers expect. A mission that would have been a rare opportunity becomes one of many. That changes negotiating power. It changes how satellite companies design programs. It changes how government agencies plan. It changes insurance assumptions. It changes the idea of what normal access to orbit looks like. The ripple effect is not just competitive, it's cultural. Spaceflight becomes less mystical. The public begins to treat launches like a regular technology service. And once the public treats something as a service, pressure increases for it to become cheaper, more reliable, more available, more scalable. SpaceX's cadence era is in effect the moment space access begins to feel like infrastructure rather than adventure. 7. The cost of cadence: complexity, pressure, and public scrutiny. A high-cadence system creates a high-pressure organization. When you launch constantly, mistakes have less time to hide. Every failure becomes visible. Every delay becomes a story. Every mishap becomes an argument about risk and responsibility. But the companies that define industries often accept this price. They become the reference point. They become the one everyone watches. They become the one everyone judges. And as SpaceX's launch cadence expands, it is increasingly judged not only as a rocket company, but as a critical node in global communications, national security logistics, and future exploration systems. That judgment is the price of dominance, and it sets the stage for the next phase: SpaceX's transition from dominant operator to space infrastructure empire, with political pressure and strategic pushback rising alongside success.
Starlink is the chapter that makes SpaceX's story bigger than rockets. With Starlink, SpaceX is not only launching payloads, it is building a global communications layer. That turns the company into something closer to an infrastructure provider, and infrastructure providers face a different world of pressure: geopolitics, dependency fears, regulation, competition from national champions, and public debates about power. Starlink is also the economic engine that changes what SpaceX can attempt. A rocket company funded purely by launch contracts must be cautious. A rocket company funded by a massive recurring service can be aggressive. This is why Starlink isn't a side business. It's a strategic pillar that shapes SpaceX's entire future. 1. Starlink as the profit engine. A key reason analysts take SpaceX's long-term ambitions seriously is that Starlink appears to generate significant profit and revenue scale. Reuters reported in February 2026 that SpaceX generated roughly $15 to $16 billion in revenue in 2025 and about $8 billion in profit, with Starlink as the main driver, accounting for a large share of total revenue. This matters because it changes what SpaceX can fund: more Starship development capacity, more launch infrastructure and production expansion, more satellite manufacturing and terminal production, more R&D for new systems and services. In other words, Starlink can fund the next generation of SpaceX without SpaceX needing to rely entirely on outside capital markets or limited government contracts. 2. Scale creates gravity, and gravity creates resistance. Once a network becomes large enough, it becomes strategically important. That importance triggers a predictable reaction. Others want alternatives. Reuters' Breaking Views described SpaceX's nascent monopoly facing a durability test as governments and competitors accelerate plans to reduce dependence on Starlink. This is not just business competition, it is national strategy. Governments don't like critical infrastructure that they don't control, and when a privately owned constellation becomes central to communications in remote areas, disaster response, defense-related connectivity, or economic development, the political temperature rises. The irony is that success invites pushback. Starlink's growth makes it valuable and makes others determined to not rely on it alone. 3. Starlink's scale is beyond a product, it's an industrial system. By 2026, Starlink is not just a network, it's a production pipeline. Satellites are manufactured, launched frequently, upgraded in generations, and replaced as newer versions become available. Public reporting illustrates the constellation's enormous scale. Space-focused outlets described the active Starlink satellite count as being in the many thousands range by early 2026, with deployments continuing at a relentless pace. This has several consequences. SpaceX can keep its rockets flying even when external demand fluctuates. SpaceX can negotiate from strength in the launch market. SpaceX can iterate satellite design quickly using the same fly-and-learn logic as rockets. SpaceX gains operational experience managing a huge distributed network. This network management capability becomes its own moat. Building a constellation is hard. Operating one reliably is harder. Scaling it into a stable service with millions of user terminals is harder still. 4. Competition forces discipline. Cyber, China, and sovereign constellations. Starlink's success sparked a new race. Reuters notes the presence of serious competitive ambitions, including Amazon's plan for a constellation of nearly 8,000 satellites by 2029 and European efforts to explore independent systems to reduce reliance on Starlink. This competitive pressure is healthy in one sense. It forces SpaceX to keep improving service quality, pricing, and reliability. But it also shifts Starlink into a mature market reality where dominance is not guaranteed by being early, it is sustained by execution. The most dangerous moment for a dominant platform is when it assumes customers have no alternatives. SpaceX's challenge is to keep Starlink valuable enough that customers choose it not because it is the only option, but because it is the best option. 5. Starlink plus SpaceX, a flywheel that competitors struggle to copy. Many companies can build satellites, fewer can launch them cheaply and frequently. Even fewer can do both and then operate the network at global scale. This is why Starlink is so strategically powerful for SpaceX. The constellation and the rockets reinforce each other. Starlink creates launch demand. Launch cadence improves reuse economics and operational learning. Lower cost and higher cadence make constellation expansion cheaper. Bigger constellation increases service capacity and revenue. Revenue funds more rocket and satellite investment. This flywheel is the SpaceX moat in its purest form, a system that gets stronger as it runs. 6. The durability test. Infrastructure companies must be trusted. Starlink's rise forces SpaceX into a new kind of responsibility. Infrastructure providers must be trusted across uptime and service reliability, user privacy and security standards, transparency around coverage and performance, lawful compliance across many jurisdictions, and careful handling of geopolitical sensitivities. This is where SpaceX transitions from fast innovator to global utility, and global utilities are judged harshly. People forgive startups for chaos. They do not forgive infrastructure for chaos. This is Starlink's great challenge, not only to expand, but to stabilize while staying affordable and competitive. 7. The bigger meaning. Starlink funds the future, but also raises the stakes. Starlink can fund Starship, lunar logistics ambitions, and long-term Mars goals, but it also makes SpaceX more visible and more politically sensitive. The larger Starlink becomes, the more it will attract regulation, scrutiny, and strategic competition. That is the paradox of SpaceX's rise in the Starlink era.
The engine that makes SpaceX stronger also makes SpaceX more contested. And that sets the stage for the next phase, SpaceX as a key partner in national exploration agendas, Artemis, lunar infrastructure, ISS deorbit planning, and the question of whether Starship becomes a reliable heavy-lift transport system rather than a brilliant prototype program.
SpaceX began as a challenger trying to reach orbit. It became a dominant launch operator. It built a global satellite network. Now it is entering an institutional phase where SpaceX is no longer judged only by its performance, but by its role in national and global space strategy. In this phase, SpaceX's rise becomes less like a startup story and more like a historical turning point, how a private company becomes essential to public goals while still trying to innovate at high speed. NASA's Artemis program is one of the most ambitious human exploration efforts in decades, aiming to return humans to the moon and build a sustained presence. In this context, SpaceX is not merely a vendor, it is a critical partner. NASA states that it will use SpaceX's Starship human landing system for Artemis 3 and Artemis 4. That line matters because it defines SpaceX's next test. Can the company translate rapid iteration culture into a system that meets the demanding, safety-focused cadence of human exploration? Human landing systems are not judged only by did it fly. They are judged by reliability, redundancy, operational procedures, failure mode management, compatibility with mission timelines, certification and review discipline. SpaceX can be fast. Now it must also be institutionally dependable. The ISS deorbit mission, the quiet proof of institutional trust. There's a certain kind of contract that signals deep trust when you are asked not to build the new thing, but to safely retire the old thing. Reuters reported NASA has contracted SpaceX to construct a spacecraft to deorbit the ISS safely at end of life. That's not glamorous compared to Mars dreams, but it is historically significant. It places SpaceX in the role of caretaker of a major human space asset, a sign that SpaceX is now embedded in the infrastructure planning of human spaceflight, not just the excitement of launches. It also shows how SpaceX's role spans generations, from delivering cargo and crew to ISS to eventually helping ensure the station's safe disposal. Starship development, high ambition, high visibility, high consequence. Starship is the pivot point that could define SpaceX's next decade. If Falcon 9 made reuse routine, Starship aims to make full-scale heavy transport reusable. The promise is civilization scale, a vehicle that can move huge mass frequently and cheaply enough to enable new categories of missions. SpaceX publishes ongoing Starship updates and test reports through its official updates page, reflecting an iterative flight test approach. Independent coverage has also described major setbacks and test failures as part of this iteration cycle. For example, Space.com reported SpaceX completed an investigation into Starship 9 failures and noted the loss of Ship 36 during ground testing following that flight period. This is not bad news in isolation, it's the cost structure of SpaceX's method. But as SpaceX becomes more institutional, the tolerance for messy iteration narrows. A private prototype culture can accept breakage. A public-facing transport system that influences national programs must eventually become predictable. The challenge is to keep the speed of innovation while steadily increasing operational reliability and safety. Why Starship is more than a rocket? It's an economic unlock. Cheaper and more frequent heavy lift could enable larger space stations and modules delivered in fewer launches, more efficient lunar cargo logistics, rapid deployment of very large satellite batches, new industrial experiments in orbit, deep space missions that require heavy payloads and refueling strategies. The long-term vision depends on more than a successful launch. It depends on repeatability. Launch, recover, refurbish, relaunch, again and again at a cadence that makes big missions practical. This is the same logic SpaceX used with Falcon 9, but the difficulty is higher by an order of magnitude. The political reality, national strategy meets private execution. As SpaceX becomes integral to Artemis and ISS planning, it steps into politics, whether it wants to or not. Reuters reported Congress is weighing extending the ISS life and mandating a lunar base under Artemis, highlighting the strategic competition framing, including efforts to counter China's increasing space capabilities. This changes the environment around SpaceX. Schedules become tied to national strategy, budgets and priorities can shift with politics, public scrutiny intensifies, international partners and rivals shape the context. SpaceX must operate inside this environment while maintaining the innovation tempo that made it successful. That's a hard balance. Many organizations slow down when politics rises. SpaceX's question is whether it can stay fast without becoming reckless. The final meaning of SpaceX's rise. If you step back, SpaceX's rise can be understood as a sequence of thresholds. Reach orbit, credibility threshold, launch reliably and frequently, operational threshold, make reuse routine, economic threshold, build a global service platform, infrastructure threshold, become a core partner in human exploration, institutional threshold. SpaceX has crossed the first four in strong form, and it is now pushing into the fifth, where the rules are stricter, the stakes are higher, and the world expects not only brilliance, but steadiness. If Starship matures into a reliable, heavy transport system, SpaceX's rise will be remembered as the moment space access began to behave like industry. If Starship remains difficult longer than hoped, SpaceX may still remain dominant through Falcon 9 and Starlink, but the timeline for space as mass transport stretches out. Either way, SpaceX has already changed the tempo of the space age. The remaining question is whether it can also change the scale.
By the time SpaceX reaches the phase you're asking to continue, the story is no longer, can they build a rocket? The story becomes, can they build an industrial system that produces deep space capability on repeat? Falcon 9 proved that rapid cadence and partial reuse can become routine. Starship is the attempt to push that logic into a new category, full-scale transport, where vehicles, engines, tanks, thermal protection, and ground systems behave less like bespoke aerospace artifacts and more like repeatable inventory. 1. The difference between a rocket program and a transport program. A rocket program can succeed with occasional flights. A transport program must succeed with frequency. It needs predictable turnaround, predictable failure rates, predictable refurbishment labor, predictable spares inventory, predictable training pipelines, predictable ground operations. In short, it needs logistics maturity. This is why Starship is not Falcon 9 but bigger. It is fundamentally different in what it demands from the organization. Bigger vehicle means bigger energy and bigger consequences for small design mistakes. Full reuse means more systems must survive harsh conditions repeatedly. Higher cadence means ground systems must be efficient, safe, and scalable. Heavy lift economics only work if refurbishment is fast and reliable, not heroic. In the same way that airlines aren't just planes, Starship is not just a vehicle, it's the whole ecosystem: production lines, launch and landing infrastructure, propellant production and storage, engine refurbishments, inspection pipelines, and mission integration processes. 2. Manufacturing philosophy. Build fast, learn fast meets build consistent. SpaceX's strongest cultural weapon has been speed.
But speed by itself doesn't create mass production. Mass production requires consistency, tight control of tolerances, weld quality, material supply, and repeatability. The Starship era is a cultural balancing act. Keep the iteration tempo that makes SpaceX dangerous, add quality systems that make SpaceX dependable at scale. This is not a trivial shift. Many engineering organizations struggle because fast and stable pull in opposite directions. Speed pushes experimentation, stability pushes standardization. SpaceX has to create a discipline where experimentation happens, but it happens in bounded layers. Early prototypes absorb risk and teach lessons. Later production blocks convert lessons into standardized parts and processes. Operational vehicles become boring because boring is reliable. The Starship as product moment is when the company stops building unique prototypes and starts building versions with clear configuration control, Block A, Block B, and so on, each one intended to be reproduced with minimal surprises. 2. The engine is the real heartbeat, scaling Raptors like jet engines. In aerospace, engines are where programs die. Engines are expensive, complex, and failure-prone when rushed. Starship's viability depends heavily on whether SpaceX can make Raptors behave like an engine fleet, produced in volume, tested quickly, refurbished efficiently, replaced modularly, improved across generations without breaking the supply chain. The leap isn't just technical, it's operational. Even if a Raptor is powerful, Starship only becomes a transport system if engine maintenance becomes predictable. If engines require slow, artisanal rebuild cycles, cadence collapses. If engines can be swapped and requalified quickly, cadence becomes possible. This is one reason Starship should be understood as an attempt to bring aviation logic into spaceflight. Create hardware designed not only to fly, but to be maintained. 4. Thermal protection problem. The reuse gate nobody can fake. Full reuse ultimately gated by re-entry and heat. Rockets can be robust in ascent, but re-entry punishes the smallest weaknesses. A fully reusable system must master thermal protection durability, tile attachment reliability, repair workflows that are fast and safe, inspection systems that catch hidden damage. The reuse gate is simple. If you can't reuse quickly after re-entry, you don't have full reuse. You have partial reuse with a slow reset. Starship's long-term hope is that tile and heat shield work becomes less manual, less time-consuming, less variable, more like aircraft maintenance intervals. This is one of the hardest parts of the entire Starship dream because it combines harsh physics with human labor. If every flight requires days of careful tile replacement, your economics and cadence suffer. The Starship era is partly an engineering war against maintenance hours. 5. Propellant logistics, turning launches into fuel logistics. At the scale Starship imagines, the limiting factor is not only vehicle readiness, it's also propellant. Huge vehicles require huge propellant flows, storage, and safe handling. This pushes SpaceX into a domain most rocket companies treat as secondary: industrial fuel infrastructure. To sustain frequent heavy launches, you need efficient loading systems, robust storage and chill-down procedures, safety systems that can run repeatedly without becoming fragile, workforce training that is consistent under high tempo, contingency operations for scrubs and delays. This is where the Starship program becomes a civilization-like logistics challenge. It starts to resemble an industrial plant as much as a launch pad. 6. The orbital refueling puzzle. Deep space becomes a logistics problem, not a rocket problem. For missions beyond Earth orbit, the big unlock is refueling. Refueling turns a single launch into a campaign. It requires reliable rendezvous and docking, transfer hardware that works in microgravity, safety protocols for cryogenic propellant transfer, and repeatable operations again and again.
In a refueling future, SpaceX must prove it can do not just one docking, but a standardized set of operations repeated many times. That's another transport system trait. The mission becomes less like a heroic one-off and more like an industrial procedure. If refueling becomes routine, then the barrier to lunar and Mars logistics shifts. The barrier becomes not can we build a rocket, but can we run a complex supply chain in orbit? 7. Why Starship is a second rise risk. SpaceX's first rise created dominance through Falcon 9 and Starlink. Starship is the attempt at a second rise, not just dominating launches, but changing what missions are possible. The danger is that a dominant company can be tempted into overconfidence. Starship must be built like a new company inside an old one. New problems, new failure modes, new constraints, new scrutiny. The program's success depends on whether SpaceX can preserve hunger and humility at the same time. 8. The hidden definition of success. Starship succeeds not when it flies once, but when it can fly often and return to flight quickly. The definition isn't spectacle, it's turnaround time. It's the difference between we landed and we are scheduled again next week. If Starship becomes a true production system, SpaceX doesn't just gain a bigger rocket, it gains something rarer, the ability to manufacture space access as a repeatable service. That would make SpaceX not merely a space company, but a transport industrial company with capabilities no historical organization has sustained at scale.
Every disruptor eventually becomes the thing it used to criticize, an institution. The question is whether it becomes a good institution or a brittle one. As SpaceX grows, it is no longer judged only by its engineering brilliance. It is judged by governance, reliability, responsibility, and the social consequences of what it builds, especially through Starlink and human spaceflight. 1. The institutional shift, from startup tolerances to infrastructure tolerances. A startup can be forgiven for chaos. Infrastructure cannot. When millions depend on your network and when government missions depend on your launch capability, your failure modes become public and political. SpaceX's institutional phase forces a new kind of excellence. Not just move fast, but move reliably. Not just innovate, but communicate clearly. Not just build, but maintain. Not just win contracts, but earn trust repeatedly. This changes the culture. It introduces more process, more compliance, more documentation. The danger is that process can smother speed. The opportunity is that process can protect mission success and public confidence. 2. Starlink as a geopolitical object. Starlink is no longer just a product, it is a geopolitical object. Once a system becomes central to communications in remote areas, disaster response, and strategic contexts, governments begin to treat it like infrastructure that must be managed, regulated, and potentially counterbalanced. This creates pressures SpaceX must navigate: licensing and regulatory compliance across jurisdictions, spectrum coordination and interference disputes, questions of access, pricing, and service continuity, demands for transparency and local partnerships, the emergence of sovereign alternatives and competitors. In a world where connectivity is power, the owner of a constellation carries influence, whether they seek it or not. 3. The astronomy and orbital environment debate. Mega constellations also trigger debates about the night sky, light pollution, and orbital congestion. SpaceX becomes part of a larger conversation. How do we balance global connectivity benefits with environmental and scientific concerns? In this institutional era, SpaceX can't treat such issues as PR problems. They become long-term license-to-operate issues. The companies that thrive in infrastructure categories are those that build credibility with stakeholders, not just customers. The deeper truth is, if your technology becomes large enough to shape the environment around it, you inherit responsibility whether you asked for it or not. 4. Safety culture, the hardest upgrade. SpaceX's greatest achievements involve risk, but human spaceflight and high-stakes national missions demand a safety culture that is both rigorous and honest. This creates a test. Can SpaceX continue to innovate aggressively while maintaining the discipline that keeps rare failures from becoming catastrophic? A mature safety culture requires transparent internal reporting without fear, strong root cause analysis practices, a willingness to slow down when data demands it, training systems that scale across many teams, clear go, no-go criteria that resist schedule pressure. The maturity move is not becoming timid, it is becoming precise. 5. The public perception problem. Trust is emotional, not mathematical. Engineers often believe trust comes from statistics. The public often experiences trust through stories. One highly visible incident can outweigh years of reliability in public memory. SpaceX must learn to manage narrative responsibility, communicate capabilities without overstating, explain failures with humility and clarity, avoid creating unrealistic expectations, show consistent improvement over time, demonstrate respect for regulators and local communities. This doesn't mean becoming boring, it means becoming credible. Credibility is the real moat for institutions. 6. Workforce and scaling, the human machine behind the rocket machine. When people talk about rockets, they forget the human system, but scale stresses human systems first. Recruiting, training, retaining, and aligning thousands of people is harder than building a prototype. The institutional phase requires SpaceX to master training pipelines that build expertise quickly, internal mobility that places talent where it's needed, clear leadership structures that prevent burnout chaos, quality systems that don't depend on heroics, cultural continuity as the company grows. One reason SpaceX has moved fast historically is that it demanded extraordinary intensity, but intensity becomes dangerous at large scale. The long game is building an organization that can sustain high performance without destroying itself. 7. Competition and national strategy. The world won't leave a single point of failure. As SpaceX becomes dominant, competitors and governments will invest heavily in alternatives, not because SpaceX is bad, but because dependency is uncomfortable. Markets and states both avoid single points of failure. This pushes SpaceX into a paradoxical role. It is the leader because it is the best operator. It is challenged because others want resilience and sovereignty. The answer for SpaceX is not to panic, it is to keep improving and to maintain partnerships that build confidence. Dominance that becomes arrogant tends to trigger backlash. Dominance that remains cooperative can endure longer. 8. The institutional success metric. In this phase, SpaceX succeeds if it becomes the default not only because it is cheap and frequent, but because it is trusted by customers, regulators, governments, scientific stakeholders, the general public. This is a different kind of excellence than early disruption. It is less glamorous, more political, and more fragile, but it is also the hallmark of institutions that shape eras.
When you zoom out far enough, SpaceX's rise becomes a question about civilization, not in a dramatic sci-fi way, but in a practical way. How does a new transportation capability reshape economics, science, security, and culture? The companies that matter most in history are those that change the default assumptions of what's possible. SpaceX has already changed one assumption, that orbital launch must be slow and expensive. The next 20 years will determine whether it changes the deeper assumption that space activity must remain limited and rare. 1. If launch becomes cheap and frequent, new markets appear. Many space markets don't exist because transport costs are too high. When costs drop, previously impractical ideas become practical. This is how industrial revolutions work.
cheaper transport unlocks new supply chains. If heavy lift and high cadence become normal, the following categories could expand: larger research platforms in orbit, more frequent science missions, scalable Earth observation and climate monitoring, rapid deployment of communication infrastructure, industrial experiments that require repeated flights, new types of satellite servicing and assembly. The key point is that space becomes less like a museum and more like a workplace. When something becomes a workplace, investment patterns change. 2. The moon as logistics, not flags. A sustained lunar presence isn't about symbolic landings, it's about logistics, delivering cargo repeatedly, maintaining infrastructure, and building operational habits. SpaceX's rise intersects this future if it can provide transport capacity that makes repeated lunar logistics affordable and frequent. If that happens, lunar activity could shift from rare missions to campaigns, and campaigns create supply contracts, maintenance ecosystems, construction operations, learning loops that reduce cost and risk over time. That's how frontier activity becomes industry. 3. Mars as a long-term supply chain challenge. Mars is not a single mission. Mars is a multi-decade logistics problem. The major hurdle is not just launching humans, it's sustaining systems, cargo, habitats, energy, life support, redundancy, and rescue options. SpaceX's Mars narrative is inspiring, but the reality is grinding. It requires reliable heavy lift, repeatable refueling operations, high confidence in re-entry and landing systems, large-scale cargo delivery before any human wave, complex supply chains on Earth feeding operations for years. If SpaceX turns Starship into an operational logistics system, Mars shifts from impossible dream to difficult plan. That is a huge difference. Civilization advances when difficult plans become executable. 4. The Starlink legacy, space as global communications infrastructure. Starlink's long-term legacy may be that it proves space-based infrastructure can be built and maintained at scale by a private company. That's a template other industries may follow, space-enabled services as normal parts of daily life. If so, the SpaceX rise is not only about exploration, it's also about everyday utility, connectivity, resilience, disaster response, and bringing service to remote places. In that future, people might not think of SpaceX as a rocket company, they might think of it as an infrastructure company that happens to launch rockets. 5. The orbital environment responsibility will define reputations. As space activity increases, managing orbit responsibly becomes central. Congestion, debris mitigation, collision avoidance, and end-of-life deorbit systems will become non-negotiable. The companies that thrive will be those that can scale responsibly without turning orbit into a junkyard. SpaceX's reputation in the long horizon will be shaped not only by how many satellites it launches, but by how well it manages the life cycle, upgrades, deorbiting, collision avoidance, and coordination with others. In a mature space economy, responsibility becomes a competitive advantage because regulators and customers will prefer operators that keep the environment usable. 6. The risk that ends dominance, complacency. The history of technology is filled with leaders who lost because they assumed their lead was permanent. SpaceX's greatest risk in the long horizon is not one competitor, it's complacency and institutional slowdown. The next SpaceX might come from a new propulsion breakthrough, radically cheaper manufacturing methods, different launch architectures, a government-backed industrial surge, novel in-orbit infrastructure that changes economics. SpaceX must keep behaving like a hungry company even as it becomes an institution. That is the ultimate cultural challenge of long-term success. 7. What history may say. If SpaceX turns Starship into a reusable transport system at high cadence, history might say SpaceX made space industrial.
If Starship remains harder than hoped, but Falcon 9 and Starlink remain dominant, history might say SpaceX built the bridge into the commercial space era. Either legacy is historically significant, but the first is civilization shaping. 8. The final rise is a character transformation. SpaceX began as a scrappy challenger. It became the high-cadence operator. It became the constellation builder. Now it must become something else, a stable institution that can still innovate. That is the ultimate continuation of the SpaceX rise, from audacious to dependable, from disruptor to infrastructure, from spectacular launches to everyday utility, from watch what we might do to this is what works repeatedly. If SpaceX can achieve that transformation, it won't just be a company with a dramatic history, it will be one of the defining builders of a new era of transportation and communication, one that extends beyond Earth.